Okay. So, yeah. So, in my last lecture, I have proved, I have finished with this group, that is An. What is An? Is the alternating group, right? Alternating group. Alternating group of order n, consisting of all even permutations. Permutations in the symmetric group Sn, right? And we have proved that this set forms a group and which is called the alternating group of order n. And most interestingly, uh, yeah, so most interestingly, we can prove that what is what what is the result? That is the number of even permutations in Sn is n factorial by 2. As we know that the number of permutations in Sn is n factorial. So we can prove that the number of even permutations in Sn is half of the number of elements in Sn. Okay. So how to prove this one? Just uh, okay. So if we can show that the number of odd permutations and the number of even permutations are same, then we are done. Since Sn constitutes of even permutations and odd permutations. That is, any permutation is either even or odd. So if we can show that the number of even permutations is equal to the number of odd permutations, then it is clear that the number of even permutations is actually half of the number of the elements of Sn. So, so, so let On be the set of all odd permutations. Odd permutations in Sn. And we have already denote uh, the set n to be the set of all even permutations. So, now we define a map phi, phi colon phi colon an to on. Okay. By the rule, what is the definition of this map? That is phi of sigma. Sigma is the is a is an even permutation. So we have to map sigma to an element in On. That is, it must be an odd permutation. Now sigma is even. So to make sigma to make the image of sigma an odd permutation, we need to multiply one transposition. So that is the trick. So what would be the transposition? The transposition is, suppose 1 2. So we multiply 1 2 with sigma. Then since sigma being an even permutation, so it is a product of even number of transposition, and we multiply one more transposition to sigma. So therefore this 1 to sigma is an odd permutation. Okay, I think it is clear. So therefore this is the map. Yeah. So this is a map. Okay. So now our aim is to show that this phi is a bijection. So which results our proof. That means the once you show that phi is a bijection, so you have proved that an, the number of elements in an, is equal to the number of elements in on. Okay. So our goal is to show that phi is 1 1 and on 2. Okay, fine. So let us check whether phi is 1 1 or not. So phi is 1 1. Why? So phi of sigma equals to phi of psi. Suppose you have two permutations, even permutations sigma and psi, and you take that their images are same. We need to check that sigma and psi must be equal. Okay. So then what you will get? So it will be 1 to phi goes to 1 to psi. Okay. Now you can check that the inverse of 1 2, the inverse permutation of 1 2, what will be the inverse permutation of 1 2? It is 1 2 again. Just compute, that is what is 1 2 permutation? The transposition, that is 1 goes to 2 and 2 goes to 1. And if you want to take the inverse, then it will be like that, 2 1 1 2, and then rearrange 1 2 2 1. So it is 1 2. Okay. So the inverse of 1 to 1 2 permutation is 1 2 itself. So therefore we would we would multiply the permutation 1 2 on both sides. So we multiply 1 2 with both this permutation. Okay. So now, so therefore, so if you multiply 1 2 with 1 2, then you will see that just since 1 2 inverse is 1 2 itself, so this will be identity E. So E phi equal to E psi. That means phi equals to psi, right? So it proves that phi is 1 1. And the next one is phi is on 2. Why it is on 2? Because suppose you take one psi belongs to ON. Okay. Now psi being a member of ON is an odd permutation. So to get an even permutation out of psi, you need to multiply one transposition to psi. And obviously we shall take the transposition 1 2. So then 1 to psi must be an even permutation, and it will be in n such that it will map to, so where will it be mapped? So it will be mapped to 1 to 1 to psi. So that means again, so being an inverse of itself, so it will be identity. So it is identity psi, that is psi. So thus we have proved that this phi is onto also. So hence the number of even permutations in Sn is equal to the number of odd permutations. And so it reflects our result. That is the number of even permutations uh, in Sn is half of n factorial. Okay, fine. Okay. Now I should mention one thing, that whenever we were talking about Zn, that is the integers modulo n, then we have seen that if you consider the multiplication modulo n, then we see that the elements for which, suppose the classes A class for which GCD of A comma n is 1, so these will form a group for any n, right? And these classes are the classes which are invertible, that means which has inverse in Zn with respect to multiplication modulo n. But one can show that, okay, the remark in Zn dot, we have seen that the set un of all classes A class for which GCD of A comma n is 1 forms a group with respect to multiplication modulo n, right? And notably, the members of un are exactly the members of Zn which has inverse in Zn dot, yes, okay. So are exactly the members of Zn which has inverses in Zn dot, right? In general, this seems to be true. And in fact, it is. And the theorem will be like that. That is, so one may state that. So one may state that, what would be the statement? So the theorem will be that suppose x dot be a monoid, right? Whenever we are talking about inverses, we need to consider monoid, since it contains identity, right? So suppose you have a monoid and suppose y be the set of all invertible elements, that is, which has inverse in x dot, elements in x dot, okay, then certainly this y forms a group with respect to multiplication, with respect to dot, with respect to dot, okay. Why? I think I need to, it would be better to leave this as an exercise. Yes. So the proof left as an exercise, just using the fact that I have stated above, this one in Zn dot. Yeah. Then this is your task for the next day. Okay. Okay, fine. Now we move towards some properties of a group. So in group, you will see some fascinating properties which are actually been studied in our earlier days, that is in our childhood days, in Z plus, in R plus, and so on. But it is true in general group. Okay, so what are those? So let me uh, properties of groups. Okay, so let me list them off, those properties. So suppose you have a group, be a group. Okay, then we see that, then we have number one. Number one, uh, inverse of A inverse is A itself for all A belongs to G. Number two, now if you take two elements A and B and take their composition AB, and then you take their inverse. But what would be the inverse of AB? This will be B inverse A inverse. This is true for all A comma B belongs to J. Number three, number three, uh, number three is uh, yeah, okay. For A comma B belongs to G, the equation Ax equal to B and xa equal to B has unique solutions. Okay. So for any A B belongs to G, the equation A dot x equal to B and x dot A equal to B has unique solutions. Okay. So let us prove one or two. I think I should leave one as an exercise. An exercise. I think you can do that. For two, now we see that whenever we are asking to find out inverse of an element, then what we do? We are just considering the equation. What is the equation? The equation is Ax equal to E, and another equation is xa equal to E, right? And we see that if this equation has solutions, then we have proved that these solutions are unique, and we have uh, we call them inverse of the element A, right? So to find out the inverse of AB, so our trick is to consider this equation for the element AB. So in place of A, we need to take AB. So take AB and then just put B inverse A inverse. Okay. Now if you can show that this is identity, and also if you take the other case also, that is B inverse A inverse dot AB is identity, then you can say that, you can conclude that B inverse A inverse must be the identity, the inverse of AB. Okay, so let us have a look. So this AB, so using associativity, we can check that yes, this holds. Now we know that B inverse B inverse, it is identity. So E A inverse, right? So that means A inverse. Whatever you multiply with identity, it will leave the same element, right? So A inverse is again identity. And also it is obvious this is also identity. And now, since the existence of inverse is unique, in a semi group, that is an algebraic system having associativity, so then so we have A B inverse is B inverse A inverse. Okay. And for the third one, so let A comma B belongs to G. Now once you choose A and B, these are fixed. And now consider the equation Ax equal to B. Then what you do? To find out the solution of this equation, so what you do, you need to find out x. So what will be x? Just take just multiply both the both sides of this equation with A inverse, right? So multiplying both sides with A inverse, we get that A inverse dot Ax equals to A inverse dot B. Now in the left side, using associativity, we will have A inverse A x equals to A inverse B. Now A inverse A is identity, so x is A inverse B. So you have found out some solution of this equation. Now you need to check whether this solution is unique or not. That is, this equation has exactly one solution, which is A inverse B. Okay. So what would be the move? So let us take, suppose you have two solutions of this equation. So let us consider two solutions. Say one is x1 and another one is x2 of this equation. Okay. Then we have, so ax1 equal to b and ax2 equal to b, right? And then we see that just ax1 equal to ax2. So from this equation, just multiply again both sides of this equation with A inverse, you will get the result. And then using associativity, so it is ex1 and it is ex2. So that means it is x1 equal to x2. So we have proved that the solutions are same. So this equation has unique solution. So in a similar fashion, the equation xa equal to b have has the unique solution x equal to b a inverse. Just multiplying both sides of this equation by a inverse, you will get your result. Okay. Now the number 4 property. Now I haven't written the fourth property because in this proof you will find something interesting. What is that? Just take this one, that ax1 equal to ax2 implies x1 equal to x2, right? Right? And in childhood we have used this one. Suppose a plus x equal to a plus y, then what you do? Just cancel out this a, right? And then you write down x equal to y. So this is the cancellation law that holds in a group. Okay. So the cancellation law, yes, that's an important one. That is, for ABC belongs to G, AB equal to AC implies B equal to C, and this one is called left cancellation. And the other one is BA equal to CA implies B equal to C, and this is called right cancellation. So in a group you can prove that these two properties holds. Okay, fine. And I would like to left this as an exercise because I have already put an indication of this proof here. Okay, fine. Okay, okay. Now one thing, okay, now one may observe that in the algebraic system z minus, right, z with respect to subtraction. Okay, we see that the equations a minus x equal to b and x minus a equal to b have unique solutions, right, in z minus. What are those? For the first one, you will have b minus a, and for the second one, you will have a plus b. Okay. Okay. Yeah. But this doesn't satisfy associativity, right? As a minus b minus c not equal to a minus b minus c, right? So it does not satisfy associativity, although it has the property 3 which a group satisfies. Okay. So if an algebraic system satisfies this property, that the equations ax equal to b and xa equal to b has unique solutions or has solutions in the algebraic system, then it doesn't imply even that it is associative, right? But interestingly, if you impose associativity with this property, with this statement, that in an algebraic system having associativity, if it satisfies the condition that the equations ax equal to b and xa equal to b has solutions in the algebraic system, then this algebraic system will be a group. So that is interesting. That is, the theorem is, suppose you have, so let us take a semi group, right? So suppose you have a semi group x dot having satisfied that for any a comma b belongs to x, the equations has ax equal to b and xa equal to b have solutions in x dot. Then you must conclude that x dot will form a group, right? This is an interesting observation, that having a subgroup which satisfies this property, that is, the equations ax equal to b and xa equal to b have solutions in x dot for any a and b belongs to the set, then that algebraic system will turn out to be a group. Okay. So how to show this one? So to prove that this will form a group, it is enough to check the existence of identity and the existence of inverse. So firstly, you need to move for searching out the identity of x dot, if it has. We do not know that it does have an identity. So we need to check, we need to show that yes, this algebraic system will have an identity. Okay. Okay. So fine. And for this one, so let A be any element X, right? Then the equation, just consider this equation, X equal to A, right? So this equation has a solution, in X dot. Say the solution is E, that is A dot E equal to A. Okay. Now this is true for A, but our claim is that this is true for any element of the set. So this is true for any B belongs to X. Why? So for this, take another B. Another element B belongs to X, right? And you have already chosen one A. And also you have chosen another B. So you have now two elements A and B. And then that equation, that is X A equal to B, has a solution in X. Say, uh, suppose it is uh, okay, suppose it is X naught. Okay, okay, that is X naught dot A equal to B. Okay, then now this will imply that now B dot E. So what is B? B is X naught dot A. X naught dot A dot E. Now you have imposed on the algebraic system the associative law. That means it is X naught dot A dot E. Now what is A dot E? A dot E is A. It is X naught dot A. So again you have the same one, X naught dot A. So this will be B. Fine. So you have proved that this implies E is the right identity, right, in X naught, X dot. So you have searched out the right identity in X dot, right? Okay. Then you need to show that this E will be the left identity also. Hmm? Right? Okay. So this, so we show that E is the left identity also. Right? Okay. Okay. Yeah. So for this one, we see that okay. For this one, we see that now a dot x equal to e. Now you have the element e, and you have already considered this a. So now you take the equation a dot x equal to e. So this has a solution in x dot. Say the solution is a dashed. That is a dot a dashed equal to e. Okay. Okay. So this proves that since the algebraic system is associative, so we have already shown that if an element has right inverse, this is a right inverse. So that right inverse is unique. So a dashed is unique and is the right inverse, right? Right inverse of a. Okay. So then using this one, we can show that yeah. Yeah. So now consider the equation a dashed a dashed a dot x a dashed a dot x equal to identity. Okay, which has a solution. A solution uh, okay, yeah, which has a solution. Suppose it is x double dashed belongs to x. So this dot x double dashed equal to identity. Okay, so now yeah, so this implies e equal to a dashed a dot x double dashed, right? Now we will see that this a dashed a is actually this one a dashed a dashed a. Why? Since a dashed a dot a dashed a equal to a dashed oh sorry yeah, so it is a dashed a. Now a dashed is identity. So it is a dashed e a. Okay, so therefore it is a dashed a, since e being the right identity. Okay, so using this fact we have put this one. So A dash A is this one. Yeah. So then, okay. So again, by associativity, we will have, so A dash A dot A dash A dot X double dash, right? What is happening here? Yes. Okay. So this is equal to, so A dash A dot, and this one is identity. So it is A dash A, right? So for any, so this implies for any A belongs to X, there exists A dash belongs to X, such that A dash equal to A dash A equal to E, right? Now you need to check that. So now E dot A, so it remains to check that E is the left identity. So what is E dash A? E can be written as A dash, right? Dot A. Now by associativity we will have A dash A, right? So again you have A dot E, and this is A. So thus this is true for all A belongs to X. So hence, while proving that E is the left identity, you have proved two things. That is, first one is A dash satisfies the property that A dash is also the element having this one. A dash A is E, right? And secondly, using that fact, you have proved that E is the, so E is the left identity. So hence in X dot. So hence, so after that, you can say that this A dash is the inverse of A. That means you have proved two things simultaneously. One is the left identity, and another one is for any A, you can have a unique inverse. And this proves that X dot forms a group, right? So during the proof, you have seen that associativity is the played the key role to get this result. Okay, and also remark is that if you observe the proof minutely, you will see that you will see one thing, that suppose if you have a semi group, right? If you have a semi group and semi group, suppose it is X dot, suppose it is X dot, X dot. Okay, so if you have a semi group having satisfied that number one, there exists E belongs to X such that A dot E A dot E equal to A for all A belongs to X, and that is E is the right identity of X dot, right? And number two is for every A belongs to X, there exists A dash belongs to X, having satisfied A dot A dash equal to E. Then you can conclude that this algebraic system will turn out to be a group. Then this will turn out to be a group. Okay. So if one starts with defining a group by the statements that an algebraic system X dot is said to be a group if it is associative, it has right identity, and it has right inverse for each element. Then these statements are sufficient to define a group. So you do not need to have both the conditions. It is enough to consider only just one-sided properties. That means an algebraic system is said to be a group if it is associative, if it has right identity, and for every element it has right inverse. Then you can say that this algebraic system is a group. Okay, fine. Yeah. Okay. And another observation is that regarding the cancellation law, that a semi group, if you have a semi group, then a semi group may satisfy both cancellation laws without being a group, without being a group. Okay, without being a group. That means we have already seen that a group must have cancellation laws, left and right both. But it says that the converse is not true in general. That is, if you have a semi group, it will satisfy, it may satisfy cancellation laws, both the cancellation laws, but it will not satisfy the properties of being a group. For example, What will be the example? Suppose, for example, okay, we have, okay, yeah, okay. So, for example, let Z plus the set of all positive integers and plus is the usual addition that we consider in the set of integers, right? The usual addition. Okay. Then you can see that this algebraic system is uh, is a semi group which satisfies which satisfies both the cancellation laws. Okay. But this will not be a group. Even you can say that this will not be a monoid, actually will not be a group, as one cannot find any identity in this algebraic system. There exists no element which satisfies the law of identity, existence of identity. Okay, so this is an example where you see that this is a semi group having satisfied the cancellation laws both, but it is not a group. Rather, it is not a monoid. Now, one may ask a question that if you have a monoid, then does it satisfy the existence of inverse to make it a group? The answer is no. There also has an example which is a monoid without being a group, but it does satisfy both the cancellation laws. Just check on your own. I am just giving you the example. Okay, you just take just I write down this one. Okay. Also note that a monoid may satisfy the cancellation laws without being a group. For example, if you consider for example, let x equal to z greater equal to 0. That is the set of all non-negative integers. That is the positive integers with 0. The set of all non-negative integers. Okay. then z greater equal to 0 with respect to plus. Now it is a monoid because you have 0 as the identity, as you have 0 as the identity, right? And also it does satisfy cancellation laws. Right? But it doesn't form a group. Why? Because no element except 0 has an inverse. No element except 0 has an inverse. Okay? Okay. Okay. So with this one, I would like to put one statement regarding these cancellation laws is that now if you confine yourself to finite sets, that is, if you have a finite semigroup satisfying both the cancellation laws, then that semigroup will turn out to be a group. It's a theorem. Okay? So, even though these are not true in general, but one may have the following interesting fact. What is that? Theorem is if x dot be a semigroup, be a finite semigroup, be a finite semigroup satisfying both the cancellation laws, then x dot will form a group. Okay? So with this one, I would like to stop for today.